Hey friend, welcome. Tonight, we'll drift through the story of Earth, from fire and stone to the world you stand on now. You don't need to stay awake. Just listen, breathe, and let science guide you into sleep. Chapter 1. Before Earth, the cosmic origins of our planet. Long before the Earth existed, before mountains rose and oceans shimmered beneath sunlight, there was only a vast, cold expanse filled with diffuse gas and dust. The story of our planet begins not with the Earth itself, but with the life and death of stars. Every element that would one day make up oceans, continents, and even human blood once burned within the hearts of ancient suns that lived and died long before our solar system was born. The universe, roughly 13.5 billion years old, had already passed through several generations of stellar creation and destruction before the small yellow star we call the Sun ever ignited. In the early epochs of cosmic history, soon after the Big Bang, the universe contained little more than hydrogen and helium, with only traces of lithium. Heavier elements, the ones necessary to build planets, did not yet exist. They were forged in the furnaces of massive stars, where nuclear fusion stitched together lighter elements into heavier ones. In their final moments, those massive stars exploded as supernovae, scattering carbon, oxygen, silicon, iron, and countless other elements into the cosmic sea. Over hundreds of millions of years, those atoms drifted through interstellar space, eventually gathering into new clouds, vast nebulae illuminated by the faint glow of starlight. Our own solar system began within one of these stellar nurseries. According to models confirmed by the study of meteorites and the physics of star formation, the Sun was born from the collapse of a giant molecular cloud. Somewhere in a spiral arm of the Milky Way, shock waves from a nearby supernova may have disturbed the balance of the cloud, causing it to contract under its own gravity. As the cloud collapsed, conservation of angular momentum caused it to spin faster, flattening into a disk, the protoplanetary disk. At its center, most of the mass gathered to form a young, glowing protostar. Surrounding it, the remaining material swirled in a vast, rotating plane of gas and dust, stretching billions of kilometers wide. Inside that rotating disk, microscopic grains of dust began to collide. Though each grain was unimaginably small, static electric forces allowed them to stick together. Over time, clumps grew into pebbles, then into boulders, and eventually into planetesimals, small irregular bodies a few kilometers across. Computer simulations and astronomical observations of young star systems today confirm this gradual coalescence. Through countless collisions, some gentle, others catastrophic, these planetesimals continued to merge, growing into the first protoplanets. In the region where Earth now orbits, temperatures were moderate enough for rocky materials like silicates and metals to condense, while volatile compounds like water and methane remained gaseous and drifted farther from the Sun. In this way, a planetary gradient took shape across the newborn solar system. The inner planets formed primarily from rock and metal, while the outer planets gathered ices and gas. The young Sun, now fully ignited, bathed its surroundings in intense radiation, driving away much of the lighter gases near the center and sculpting the final architecture of the system. The material that would become Earth passed through countless transformations during this era. Every atom in your body, every oxygen atom you breathe, every calcium atom in your bones, every carbon atom in your cells was once part of interstellar dust enriched by generations of stars. This realization, supported by isotopic analyses of meteorites and cosmic dust particles, is more than poetic, it is empirical. The isotopic ratios of oxygen, carbon, and nitrogen in primitive meteorites match those found in the solar system, suggesting a shared stellar ancestry. As the young sun matured, the inner disk began to thin. Within a few million years, only planetesimals and growing planetary embryos remained, colliding and merging in a violet ballet. This stage, known as the late heavy accretion, defined the early solar system's structure. Each collision released tremendous heat, melting rock and metal, vaporizing water, and sometimes even stripping entire atmospheres. Through this process, Earth's building blocks gathered mass and energy until gravity pulled them into a roughly spherical shape. Around this same time, another event of monumental consequence took place. A protoplanet, roughly the size of Mars, named Theia by modern astronomers, collided with the proto-Earth. The impact was so immense that both worlds partially vaporized. For a brief period, Earth's surface turned into a global ocean of molten rock, and debris from the collision was thrown into orbit. Over time, that debris coalesced to form the Moon. The isotopic composition of lunar rocks, almost identical to that of Earth's mantle, confirms this shared origin. This impact also tilted Earth's axis, giving rise to the cycle of seasons that would later shape life's rhythms. When the molten Earth began to cool, its heavier elements, such as iron and nickel, sank toward the center, forming the core. This differentiation released even more heat, sustaining magma oceans for tens of millions of years. The lighter silicate minerals floated upward, creating the mantle and the first thin crust. Although no rocks remain from this earliest epoch, evidence from ancient zircon crystals, tiny mineral grains older than 4 billion years, provides clues about conditions then. These zircons suggest that liquid water already existed on the surface within a few 100 million years after Earth's formation, hinting that oceans may have condensed surprisingly early. The origin of Earth's water remains one of the most fascinating puzzles in planetary science. Some of it likely came from volatile compounds trapped in the original dust grains of the protoplanetary disk. Yet a significant fraction may have been delivered later by comets and asteroids rich in ice. Studies comparing hydrogen isotopes in ocean water and meteorites reveal that many carbonaceous chondrites, a type of primitive asteroid, have compositions strikingly similar to Earth's water, implying that much of it came from these rocky messengers from the outer solar system. As Earth stabilized, its surface continued to change under relentless bombardment from smaller asteroids. These impacts sterilized the crust repeatedly, reshaping continents before they even existed. At the same time, the planet's interior remained hot, driving powerful volcanic activity. Volcanic gases, carbon dioxide, nitrogen, water vapor, and traces of sulfur escaped into the forming atmosphere. This early atmosphere was dense and toxic, a far cry from the breathable air of today. Without oxygen, it consisted largely of carbon dioxide and nitrogen, shrouding the young planet in a haze. From a cosmic perspective, this violent beginning was not unique. Across the galaxy, astronomers have observed young planetary systems undergoing similar stages of formation. The dusty disks around stars such as HL Tauri or Beta Pictoris show gaps and rings carved by forming planets, snapshots of worlds in their infancy. These observations confirm that the processes that shaped Earth are part of a universal pattern, governed by the same laws of gravity and thermodynamics that operate everywhere in the cosmos. By the time the solar system settled into its present configuration, the inner planets, Mercury, Venus, Earth, and Mars, had taken shape. Farther out, the gas giants Jupiter and Saturn dominated, their immense gravity influencing the orbits of everything around them. Beyond them lay Uranus and Neptune, composed mostly of icy materials, and beyond even those, the remnants of the protoplanetary disk drifted as comets in the Kuiper belt and Oort cloud. Earth, meanwhile, was entering a quieter phase, ready for the next stage of transformation, from molten world to a place where life could begin. The physics that underpins this evolution is remarkably elegant. Gravitational collapse, conservation of angular momentum, radiative transfer, and nuclear fusion all emerge from the same physical principles that we study in laboratories and telescopes today. Spectroscopic observations of other star-forming regions, such as the Orion Nebula, reveal the same spectral fingerprints of hydrogen and dust that once filled our own cosmic cradle. The temperature gradients, pressure waves, and accretion flows modeled by astrophysicists describe precisely how disks evolve into stars and planets. In this sense, the story of Earth's birth is not only history, it is a living example of universal physics at work. Yet there is also a fragile beauty in this story. The formation of a habitable world required extraordinary coincidence, the right distance from its star, the right chemical ingredients, the protection of a magnetic field, and a companion moon to stabilize its rotation. Each of these conditions traces back to those first moments in the collapsing nebula, when random fluctuations determined where material gathered and where it did not. In the dance of gravity and time, the seeds of habitability were planted long before any ocean shimmered or any breeze moved across the land. Eventually, the light from the sun began to stabilize, and the violent impacts grew less frequent. The crust solidified, the oceans condensed, and the sky, though still alien, began to clear. It was on this foundation that the next great chapters of Earth's story would unfold. The formation of continents, the emergence of an atmosphere capable of supporting life, and the long, slow evolution that would lead from simple molecules to complex consciousness. To gaze back upon this time is to recognize that everything we see around us, the air we breathe, the water we drink, the soil beneath our feet, arose from cosmic processes spanning billions of years. The atoms in your body were once part of a star that died to make way for new worlds. You are, in every sense, made of stardust, reorganized into awareness. And as the day ends, and you let your thoughts drift like dust in that ancient nebula, you might imagine the soft hum of creation still echoing across time. The same forces that shaped galaxies also shaped you. The same cosmic dust that gathered into planets now rests quietly in your hands. In the vast silence of the universe, Earth became possible, and so did you. Breathe softly and let the enormity of that truth carry you into calm. You are part of the story that began before worlds had names, and it is still unfolding gently within you. Chapter 2. Birth from Fire, the Making of a Planet. When the young sun first blazed to life, the solar system was a turbulent sea of gas, dust, and radiation. In that chaos, through the slow mathematics of gravity and the patience of time, Earth began to take shape. It was not a gentle birth, but a violent one, an era defined by collisions, melting, and transformation. The planet we now call home was forged in fire. In the beginning, the inner solar system was filled with rocky debris left over from the sun's formation. The outer regions, cold and rich in ice, had already begun forming the gas giants, but near the sun, only silicates and metals could survive the heat. Temperatures in the disk soared high enough to vaporize most volatiles, stripping the region of water and carbon compounds. What remained were grains of dust and fragments of metal. Tiny, resilient pieces of matter that would one day become the building blocks of worlds. The process of planetary formation was both simple and profound. Dust grains collided gently at first, clinging together by static forces. Over time, the clumps grew larger, becoming pebbles, then boulders, and finally kilometer-wide planetesimals. Gravity took over from there, pulling these bodies toward one another in increasingly energetic impacts. The solar system became a cosmic construction site, its materials colliding, breaking apart, and reassembling over and over again. As the proto-Earth grew, each collision released enormous amounts of heat. The surface melted repeatedly, forming vast oceans of magma that glowed in the light of the newborn sun. Within this molten world, a process known as differentiation began. Heavier elements such as iron and nickel sank toward the center, forming a dense metallic core, while lighter silicate materials floated upward to create the mantle and crust. The chemical layering that defines Earth today was established in those early chaotic epochs. The formation of the metallic core did more than separate elements. It generated the foundation for Earth's magnetic field. As molten iron churned deep within, it produced electric currents that gave rise to a protective magnetic bubble. Though weak at first, this early magnetosphere would later become the planet's shield against the solar wind. Without it, the atmosphere could have been stripped away, leaving Earth barren like Mercury. Around this time, a monumental collision reshaped the young planet's destiny. A Mars-sized body, which scientists call Theia, is thought to have slammed into the proto-Earth. The energy released from that impact was beyond comprehension, enough to melt much of both worlds and vaporize vast amounts of rock. The impact tore away material from Earth's mantle, sending it into orbit as a glowing ring of debris. Over the course of thousands of years, that ring coalesced into the moon. The isotopic fingerprints of Earth and the moon, nearly identical in composition, confirm their shared origin. This collision not only created the moon, it transformed the Earth. The immense impact tilted the planet's axis, giving rise to the seasonal rhythms that would later shape the cycles of life. The moon's gravitational presence also slowed Earth's rapid rotation, lengthening the day and stabilizing the planet's tilt. Without the moon, Earth's climate might have swung chaotically between extremes. After the impact, Earth's surface was once again an ocean of fire. The crust was obliterated, the atmosphere vaporized. For millions of years, the planet glowed red, its molten surface radiating heat into the blackness of space. Slowly, as the energy dissipated, silicate minerals began to crystallize, forming a new, thin crust. Volcanoes burst through it constantly, releasing water vapor, carbon dioxide, and nitrogen into the air. The first atmosphere was thick and suffocating, a blanket of gases without a trace of oxygen. The cooling continued. Steam condensed into rain, and the rain fell for centuries, filling the first basins and depressions with liquid water. Oceans were born out of vapor and lightning, spreading across the still scarred surface. Some of that water likely came from volcanic outgassing. Some may have been delivered by asteroids and comets rich in ice. The evidence lies in hydrogen isotope ratios. The water locked inside ancient meteorites closely matches that of our oceans, suggesting that the same cosmic chemistry shaped them both. Water quickly became one of Earth's great stabilizers. It absorbed and distributed heat, softened the young planet's climate, and began dissolving carbon dioxide from the air, forming carbonates on the seafloor. This process, primitive though it was, marked the beginning of Earth's long climatic balance, a natural feedback between ocean and sky that still regulates temperature today. Deep below the surface, the core remained molten, driving powerful convection currents in the mantle. These movements pushed and fractured the crust, creating a primitive form of tectonic recycling. Although true plate tectonics would take much longer to develop, even this early motion helped regulate internal heat and maintain chemical diversity on the surface. Islands of granite-like rock called cratons floated on the molten sea below. They would drift and merge over eons, forming the continents we now know. But in these early days, stability was fleeting. The solar system was still crowded with debris left over from planet formation. Asteroids and comets frequently collided with Earth, blasting craters thousands of kilometers wide. This relentless bombardment, known as the Late Heavy Bombardment, lasted hundreds of millions of years. Each impact released more heat, melting parts of the crust, evaporating oceans, and sterilizing the surface again and again. The scars of this era remain visible on the Moon, whose unchanging face preserves the record of a time when the inner planets endured constant assault. Despite the violence, life's future ingredients were gathering. Meteorites carried not only water, but also carbon compounds, organic molecules like amino acids, that would one day serve as the raw materials for biology. The planet, though scorched and unstable, was being prepared chemically for what would come next. As the bombardment waned, Earth's crust thickened and its internal heat flow diminished. The skies began to clear of debris, allowing sunlight to reach the surface. Lightning danced through volcanic clouds, charging the air and sea with energy. The world remained alien, its oceans black with dissolved minerals, its atmosphere tinted orange by methane and carbon dioxide. Yet within this strange environment lay the potential for chemistry to organize itself into something more. Scientific evidence for these stages comes from many sources. Ancient zircons that survived from the Hadean eon, isotopic studies of meteorites, and models of planetary formation tested through supercomputer simulations. Meteorites known as chondrites, unchanged since the birth of the solar system, contain the same elemental ratios found on Earth, confirming our planet's shared origin with the rest of the solar system's material. Seismic data reveal the layering created during early differentiation, and magnetic studies trace the ongoing motion of Earth's molten core. Every piece of data reinforces the same story. Our world was born not by chance, but through the natural unfolding of cosmic physics. The processes we can only imagine from deep time are visible in other corners of the galaxy today. Telescopes like ALMA and the James Webb Space Telescope have captured images of protoplanetary disks around young stars, rings of dust and gas marked by dark gaps where new planets are forming. These snapshots are windows into our own past, showing that the creation of worlds is not unique but universal. Everywhere gravity reigns, matter gathers, collides, and ignites into the endless cycle of destruction and rebirth that gives rise to planets like ours. And yet, even with all this knowledge, there remains something quietly humbling about the thought that Earth's calm landscapes, blue oceans, and drifting clouds began in such chaos. Every pebble and grain of sand was once molten. Every drop of water has been vapor, rock, or ice many times over. The same processes that shaped mountains and seas also set the conditions for life to emerge. When we look at the moon, we are seeing not a distant body, but a reflection of that ancient impact, a monument to the violence that made stability possible. The moon's steady pull continues to sculpt our tides and regulate the slow rhythm of the planet's spin. Even in its silence, it reminds us of how interconnected the solar system's events truly are. The Earth's story is a story of opposites, of fire and water, destruction and renewal, chaos and balance. It began as molten rock and metal, yet somehow became a cradle for life and thought. From the perspective of cosmic time, that transformation seems miraculous, but it is simply the outcome of the laws of nature operating across billions of years. When the night grows quiet and you feel the weight of the day ease away, remember that the ground beneath you was once liquid fire. The elements within you, iron in your blood, calcium in your bones, once flowed together in that molten ocean. You are the calm that came after creation's storm. You are part of the cooling of the universe. Close your eyes and imagine that ancient world glowing beneath a dark sky, a world still becoming. The same heat that once burned across its surface still lingers deep below, in the slow heartbeat of the mantle, in the warmth that radiates through stone. The Earth's fire never died. It simply settled into balance, and from that balance came everything: oceans, air, forests, thought. The planet born from fire became the world that dreams. Chapter 3. The Hadean Earth, Oceans, Atmosphere, and the First Stability. When the fires of Earth's violent birth finally began to fade, the planet entered a new and mysterious era. It is called the Hadean Eon, a name drawn from the ancient Greek underworld, not because the Earth was dead, but because it was still emerging from a state of infernal transformation. Between roughly 4.5 and 4 billion years ago, the Earth was unlike anything we can imagine today. Its surface a mosaic of molten rock, oceans of vapor, and skies filled with toxic gases. Yet within this chaos, the first traces of stability began to take hold. The Hadean marks the transition from a planet that was molten and unstable to one that could host oceans, continents, and eventually life. No rocks survive intact from this time. The Earth's earliest crust has long since been recycled by geological processes, but within ancient zircon crystals, tiny, nearly indestructible minerals that can survive billions of years, scientists have found time capsules from this lost world. Analyses of these zircons, discovered in Western Australia, reveal that by around 4.33 billion years ago, Earth already had solid crust and liquid water on its surface. From these microscopic witnesses, we know that even in its earliest age, the planet had begun to cool and differentiate. After the colossal impact that created the moon, the surface of Earth had been completely molten. Over millions of years, heat escaped into space, and the magma oceans slowly crystallized. Heavy minerals sank into the mantle, while lighter silicates formed the first crust. The atmosphere at this stage was dominated by volcanic gases, carbon dioxide, nitrogen, water vapor, and traces of sulfur and methane. There was no oxygen, no ozone layer, and no blue sky. The sun shone dimly through a thick orange haze, and the air was far denser than today's, pressing down upon the newly formed surface. Volcanoes were constant, belching gas and molten rock from the deep interior. Each eruption added more carbon dioxide and water vapor to the atmosphere, creating an intense greenhouse effect. The heat trapped by these gases slowed the cooling of the surface, yet as time passed, the balance shifted. The planet radiated energy into space faster than it received it, and the first signs of equilibrium began to appear. Eventually, the temperature dropped low enough for water vapor to condense. For thousands of years, torrential rain fell from the sky, steaming as it met the hot crust, hissing through cracks in the newborn continents. The oceans that formed were unlike ours, dark, mineral-rich, and acidic, but they were the first stable bodies of water on the planet. They pooled in low basins, cooled the crust, and began dissolving carbon dioxide from the air, helping to regulate the planet's temperature. In this way, Earth's first climate system was born, a self-correcting feedback between ocean, rock, and atmosphere. Some of that water likely came from volcanic outgassing, released from deep within the mantle. But isotopic studies of hydrogen in ancient minerals show that a portion may have been delivered by asteroids rich in hydrated minerals, the remnants of the early solar system. The hydrogen-deuterium ratios in ocean water and certain meteorites match closely, suggesting that our oceans were seeded from both terrestrial and cosmic sources. The very water that fills Earth's seas and moves through our own cells may thus be older than the planet itself. Beneath these first oceans, the crust began to evolve. The initial crust was probably mafic, dark, dense, and rich in magnesium and iron. But as partial melting continued in localized regions, lighter continental material began to accumulate. These patches of proto-continental crust, composed mostly of granitic rocks, floated higher than their surroundings, like islands amid the darker oceanic plains. Although they were small and unstable, they were the first hints of continents, and they marked the beginning of the geological diversity that defines Earth today. At the same time, the planet's interior remained hot. The decay of radioactive elements and residual heat from formation kept the mantle in constant motion. Convection currents transported energy upward, driving volcanic activity and reshaping the crust. Even without fully developed plate tectonics, this circulation was already recycling material between surface and depth, ensuring that no part of the early crust remained static for long. The atmosphere of the Hadean Earth was thick and alien. Carbon dioxide likely dominated, providing the greenhouse warmth that kept the planet's surface from freezing under a fainter young sun. The early sun was about 30% dimmer than it is today, yet geological evidence shows that liquid water persisted. This apparent contradiction, known as the faint young sun paradox, is explained by the dense greenhouse atmosphere that trapped heat efficiently. Methane, produced by volcanic reactions and possibly by lightning-driven chemistry, may also have contributed. High in the sky, clouds of dust and gas absorbed and scattered sunlight. Lightning illuminated the storms, and meteorites frequently streaked through the air as the planet continued to sweep up debris from space. Each impact released tremendous energy, sometimes vaporizing entire sections of ocean and atmosphere. During the first few 100 million years, Earth was struck repeatedly by asteroids and comets, a period known as the Late Heavy Bombardment. Though catastrophic, these collisions helped shape the planet's chemistry. They delivered additional volatiles, stirred the mantle, and perhaps created the hydrothermal systems that would later become havens for emerging life. Beneath the oceans, geothermal energy drove convective currents. Along ridges and cracks in the crust, superheated water circulated through newly formed rocks, dissolving minerals and releasing gases. These hydrothermal vents were likely common across the Hadean seafloor, creating rich chemical environments filled with gradients of temperature and energy. Though life had not yet begun, such environments would one day become the cradles of biology, natural laboratories where chemistry could experiment with complexity. The first chemical cycles were already underway. Carbon dioxide from volcanoes dissolved in rainwater and oceans, forming weak acids that reacted with rocks to produce carbonates. These reactions slowly removed carbon from the atmosphere, locking it into the crust. In turn, volcanic activity released it again, maintaining a long-term balance. Even in this early state, Earth was establishing the feedback systems that would allow it to remain habitable for billions of years. The formation of the oceans also changed the face of the planet in another way. It altered how heat moved through the surface. Water carried energy far more efficiently than rock or air, spreading heat across vast areas and moderating temperature extremes. This dynamic created zones of relative calm, regions where the temperature remained stable enough for chemical reactions to persist. Over time, those stable conditions would prove essential to the emergence of life. Meanwhile, the planet's magnetic field, born deep in the metallic core, continued to strengthen. Evidence from magnetic minerals trapped in ancient rocks shows that Earth's magnetic field has existed for at least 4 billion years. This invisible shield deflected much of the solar wind, preventing the atmosphere from being eroded by charged particles from the sun. Without it, the volatile compounds that made oceans and air possible would have been lost to space, as happened on Mars. The Hadean Earth was still dangerous, but it was no longer hellish. The surface had cooled, the crust thickened, and the oceans shimmered beneath a hazy sky. The planet was restless but beginning to find balance. Each process, volcanic, chemical, atmospheric, fed into the others, forming a complex, self-sustaining system. Earth was, in essence, learning how to maintain itself. Though no life stirred yet, the chemistry of life was already forming. Lightning and ultraviolet radiation split atmospheric molecules, creating reactive fragments that combined into organic compounds. These compounds fell into the oceans, where they accumulated and interacted with minerals and heat from the seafloor. The building blocks of biology, amino acids, nucleotides, and lipids, were forming in countless variations. Nature was experimenting on a planetary scale, preparing the groundwork for what would come in the Archean eon that followed. From a scientific perspective, the Hadean is one of the most difficult chapters in Earth's history to study because so little physical evidence remains. Yet every piece of data points to the same picture. A dynamic, evolving world that moved from molten instability toward enduring equilibrium. Models of thermal evolution, isotope analyses of ancient zircons, and the study of other rocky planets all reinforced this narrative. The Hadean Earth was not a static wasteland, but a living, breathing system in its infancy. To imagine this world is to witness the first balance between chaos and calm. A dim sun hung in a copper sky. Volcanoes fumed along vast coastlines. Oceans steamed, their surfaces broken by meteoric impacts that sent waves of vapor into the air. And yet, within that seeming disorder, stability was taking shape. The temperature had reached a point where water could remain liquid. The crust could persist. The magnetic field could endure. These conditions would not vanish again. The planet had passed through its trial by fire and now stood on the threshold of habitability. Every later chapter of Earth's story, Its continents, its atmosphere, its biosphere emerged from this foundation. The balance established during the Hadean continues to define the planet's behavior. The same processes that cooled the magma still regulate the deep mantle today. The same cycles of carbon, water, and heat that stabilized the young Earth remain active in our own time. The echoes of that ancient equilibrium are all around us, in every ocean current and cloud. And perhaps that is what makes this epoch so quietly profound. Out of fire and bombardment came balance. Out of chaos came continuity. The Earth, once molten and airless, became a place where water could flow and chemistry could dance. When you listen to the sound of rain against a window, you are hearing the same process that began more than 4 billion years ago. The condensation of vapor into drops, the endless recycling of water through sky and stone. When you feel the ground beneath your feet, you are standing on the cooled crust that first solidified in the Hadean age. You are surrounded by the stability that the planet fought to achieve across billions of years. And as night falls, imagine that ancient world, the dim sun, the steaming seas, the silence before life began. The same planet turns beneath you still, its deep rhythms unchanged. From that early heat and pressure came oceans, air, and time itself. The world learned how to last, and within that endurance, consciousness would one day awaken. Chapter 4. The Archean Dawn, when life first stirred. By the time the Hadean eon gave way to the Archean, Earth had survived its most violent beginnings. The surface was no longer a molten expanse, but a landscape of rock and water, its crust stable enough to support the slow work of time. The Archean, spanning from about 4 billion to 2.5 billion years ago, was an age of transformation. A time when the planet's restless chemistry began to organize itself into something new. It was during this eon that life first appeared, quietly altering the destiny of the world. The conditions were still far from gentle. The sun shone weaker than it does today, delivering barely 70% of its current energy. The atmosphere remained thick with carbon dioxide and methane, sustaining a strong greenhouse effect that compensated for the faint sunlight. Oxygen was still absent, and the sky likely appeared orange or pale brown, filled with organic haze produced by ultraviolet radiation striking methane molecules. The oceans, vast and dark, were rich in dissolved iron and minerals leached from volcanic rocks. The continents were smaller, scattered across the globe as volcanic islands and microcontinents drifting atop an oceanic crust. And yet, despite this seemingly alien environment, the chemistry of life began its intricate dance. How that dance began remains one of science's greatest mysteries. Several hypotheses compete to explain the origin of life, and all draw from the same fundamental principle: that simple chemistry, given enough time and energy, can give rise to complexity. One leading idea places life's cradle in the deep ocean, near hydrothermal vents. These vents, discovered in the modern seafloor, release mineral-rich water heated by the planet's interior. They create environments with strong chemical gradients, differences in temperature, pH, and composition that can drive the spontaneous formation of complex molecules. Laboratory simulations show that such conditions can produce amino acids, lipids, and even simple RNA-like chains. The Archean seafloor may have been covered with such vents, each a natural reactor experimenting with combinations of chemistry. Another possibility suggests that life began in shallow, warm ponds at the edges of volcanic islands. As water evaporated under the sun's heat, It could have concentrated organic molecules, allowing them to form membranes and primitive metabolic cycles. Lightning, ultraviolet light, and geothermal energy provided the sparks of activation, helping molecules join and replicate. Whether deep beneath the sea or on sunlit shores, the crucial transition occurred when chemistry learned to copy itself, when certain molecules began to preserve their structure across generations. Evidence for early life in the Archean comes not from fossils of organisms, but from subtle chemical signatures preserved in ancient rocks. In regions such as Western Australia and Greenland, geologists have discovered layers of carbon-rich sediments whose isotopic ratios differ from those produced by purely geological processes. The lighter isotopes of carbon, those favored by living metabolism, appear in abundance, suggesting that by around 3.5 billion years ago, microbes were already drawing energy from their surroundings. Microscopic fossils from similar-aged rocks provide further clues. In Western Australia's Pilbara Craton, thin sections of ancient stromatolites, layered domes of sediment, record the earliest visible traces of life. These structures, built by colonies of microorganisms, most likely cyanobacteria, grew as thin mats that trapped and bound sediment grains. Over time, their slow, rhythmic growth built towers and domes that still survive in some modern shallow seas. These microbial communities were the first ecosystems, transforming sunlight and chemistry into energy. Yet the early biosphere was unlike today's. The Archean atmosphere contained almost no oxygen, and the oceans were filled with dissolved iron and sulfur. Many microorganisms that thrived in these conditions were anaerobic, meaning they did not require oxygen to survive. Instead, they used chemical reactions involving hydrogen, sulfur, or methane to extract energy. These metabolic pathways, though primitive, were astonishingly efficient, and they laid the groundwork for the biochemical diversity that would follow. At some point, probably by the middle of the Archean, a remarkable innovation occurred: the evolution of photosynthesis. The earliest forms may not have released oxygen. They likely used hydrogen sulfide or other compounds as electron donors. But eventually, a lineage of microbes, ancestors of modern cyanobacteria, learned to use water in the process, splitting it and releasing oxygen as a byproduct. This seemingly simple adaptation would change the planet forever. Initially, the oxygen produced by these early photosynthesizers did not accumulate in the atmosphere. It reacted immediately with the iron dissolved in the oceans, forming rust-colored minerals that sank to the seafloor. These deposits, known as banded iron formations, can still be seen today as alternating red and gray layers in ancient rocks. They record the slow saturation of the oceans with oxygen, a process that took hundreds of millions of years. During this time, the biosphere and the planet's geology became intimately linked. Microbes interacted with their environment in ways that stabilized climate and shaped the chemistry of the air and sea. Methane produced by certain bacteria contributed to the greenhouse effect, helping to keep the planet warm despite the faint sun. Others recycled nitrogen and sulfur, maintaining essential nutrient cycles. The Earth was becoming a self-regulating system, a complex feedback loop between life and environment that would persist for the rest of geological history. The continents of the Archean were also evolving. Heat from the planet's interior drove intense volcanic activity, and the first true continental crust began to stabilize. Granite-rich regions known as cratons formed the seeds of future landmasses. Around their margins, island arcs and subduction zones recycled oceanic crust, creating the earliest examples of plate-like behavior. Over time, these fragments collided and merged, forming larger continental blocks. The interaction between geology and atmosphere shaped the global environment. Volcanic gases fed the air, while erosion and chemical weathering influenced ocean composition. The oceans themselves were dynamic. They may have been slightly warmer than today's and were often tinged green or reddish-brown by iron and microbial pigments. The tides, driven by a moon much closer to Earth than it is now, were stronger, pulling water hundreds of kilometers across coastlines and mixing nutrients into the shallows. It was in these fluctuating environments, neither fully stable nor wholly hostile, that life diversified. Some of the earliest microbial gnats colonized shallow waters near volcanic shores. There, sunlight, minerals, and warmth provided the perfect balance for metabolic experimentation. These gnats grew slowly, millimeter by millimeter, forming layered colonies that altered their environment in subtle ways. They produced oxygen locally, changed the chemistry of nearby sediments, and left behind patterns that still mark ancient rock surfaces today. In their quiet persistence, these early organisms began a process that would eventually transform the entire planet. As oxygen built up in local environments, it triggered new evolutionary challenges. Oxygen is highly reactive. It can destroy organic molecules as easily as it fuels metabolism. Some microbes evolved ways to detoxify it, leading eventually to the development of aerobic respiration, a process that yields far more energy than anaerobic reactions. This innovation, though small in scale, set the stage for future complexity. By the end of the Archean eon, around 2.5 billion years ago, the balance of Earth had shifted once again. The crust had thickened, continents had grown, and the biosphere was no longer merely a chemical curiosity. It had become a global force. The slow release of oxygen into the oceans and atmosphere prepared the way for the great oxygenation event that would define the next eon. The Proterozoic. Life had learned not only to survive, but to shape the planet that hosted it. Scientific evidence for this transformation continues to grow. Carbon isotope studies, sulfur fractionation patterns, and microfossil analyses all point to biological activity deep in the Archean past. In Greenland and South Africa, rocks older than 3 billion years preserve subtle textures consistent with microbial films. In the laboratory, researchers replicate early Earth conditions and watch organic molecules assemble spontaneously into membranes and self-replicating systems. While no single experiment has recreated life's origin, together they confirm that the transition from chemistry to biology was not impossible, only improbable, and yet inevitable, given enough time. The Archean Earth would have looked strange to our eyes, a world of steaming seas and crimson skies, continents cloaked in volcanic haze, and a sun dimmed by methane fog. And yet beneath those skies, invisible to any observer, life had taken hold. It spread across the oceans in forms too small to see, multiplying, mutating, and weaving itself into the planet's fabric. The soundless ripples of this microscopic revolution would eventually echo through everything that followed. The rise of oxygen, the emergence of complex cells, and the appearance of multicellular life, hundreds of millions of years later. When we trace our origins back through time, we arrive here, at this quiet dawn when life first stirred. Every cell in your body carries the legacy of those early microbes, the same fundamental chemistry, the same genetic code refined through endless generations. The air you breathe owes its composition to their work. The rocks beneath your feet bear the minerals they precipitated. The entire planet bears their signature. And yet, despite their tiny size and ancient age, they remind us of something universal, that life is the universe's way of remembering itself. From the blind interplay of molecules came awareness, curiosity, and reflection. The Archean Earth did not know that it was alive, but through us, it can now look back and recognize its own beginning. So when you stand by the ocean and watch the waves move under the sun, you are seeing the same rhythm that began billions of years ago, the rhythm of a world that learned to live. Every breath you take connects you to those first microbes in the ancient sea. And somewhere deep within you, their persistence endures. The quiet memory of the Archean dawn when life first stirred and the earth began to dream. Chapter 5. The Great Oxygenation, when the air turned toxic. By the close of the Archean eon, Earth was already alive in a quiet microbial way. Across the oceans, mats of bacteria covered shallow seafloors, feeding on light and minerals, transforming the planet's chemistry cell by cell. For hundreds of millions of years, life remained small, simple, and self-contained, content to thrive in the ancient seas. But beneath this apparent stillness, an invisible revolution was building. Through a process both creative and catastrophic, those tiny organisms would remake the world. The air itself would change, and the transformation would come at a cost so great that it nearly extinguished life altogether. This was the Great Oxygenation. The story begins with a single, extraordinary innovation: oxygenic photosynthesis. Earlier forms of photosynthesis, which had existed for much of the Archean, used hydrogen or sulfur compounds to capture sunlight's energy. But some microbes, ancestors of what we now call cyanobacteria, discovered a more abundant source of electrons: water. By splitting water molecules with sunlight, they gained access to a nearly limitless energy supply. The waste product of that reaction was oxygen, a molecule that would become both the breath of future life and the scourge of the world that came before it. At first, the oxygen released by these early cyanobacteria had nowhere to go. The oceans were filled with dissolved iron and other easily oxidized elements. Each molecule of oxygen reacted immediately, binding with iron to form insoluble oxides that sank to the seafloor. Over countless centuries, these reactions produced the vast banded iron formations we still find today in rocks from Australia, North America, and South Africa, alternating layers of red and gray that record the slow saturation of the oceans. For millions of years, this process continued unseen. Oxygen was produced and consumed in balance, never accumulating in the atmosphere. The planet remained largely anoxic, without free oxygen, because the oceans act as a chemical sponge. But as cyanobacteria spread and multiplied across the shallow seas, the balance began to shift. The available iron in the oceans was gradually used up, and the oxygen they produced started to escape into the air. The timing of this turning point, around 2.5 billion years ago, marks the transition from the Archean to the Proterozoic eon. Geological evidence, particularly from sulfur isotopes, shows that something profound occurred. Oxygen began to build up in the atmosphere for the first time in Earth's history. The Great Oxygenation event, as it is now known, fundamentally altered the chemistry of air, water, and life itself. From a chemical perspective, oxygen is one of the most reactive elements in the universe. It readily combines with metals, gases, and organic molecules, releasing energy in the process. For the anaerobic organisms that dominated the Archean world, this made it deadly. Oxygen disrupted their metabolism, damaged their cellular structures, and oxidized the molecules they depended on for survival. To them, it was a poison, not a gift. As oxygen levels rose, vast ecosystems of anaerobes began to collapse. Some retreated into the oxygen-free depths of sediments or the dark interiors of rocks. Others adapted, evolving new ways to cope with the toxin. A few lineages discovered a remarkable alternative. Instead of merely surviving oxygen, they learned to use it. These were the ancestors of aerobic organisms, life forms that harnessed oxygen to extract far more energy from food than anaerobic metabolism ever could. This innovation would later enable complex life, but at the time it was a rare adaptation in a hostile new world. The transformation of the atmosphere also triggered profound geological and climatic changes. As oxygen accumulated, it reacted with methane, which had been one of the planet's dominant greenhouse gases. Methane is far more efficient at trapping heat than carbon dioxide, and its removal caused a dramatic cooling. With less methane to warm the surface, global temperatures dropped, and Earth may have entered its first great ice age. Some geologists believe that large parts of the planet froze over during this period, perhaps even becoming what is known as a snowball Earth, where ice reached the equator. At the same time, the newly oxygenated air began to form another protective layer, the ozone layer. High in the atmosphere, ultraviolet light from the sun broke apart oxygen molecules and allowed them to recombine as ozone, a molecule composed of 3 oxygen atoms. This fragile shield absorbed much of the sun's harmful ultraviolet radiation, preventing it from sterilizing the surface. Without this development, complex life could never have moved onto land in the eons to come. The Great Oxygenation was not a single event, but a drawn-out process lasting hundreds of millions of years. Oxygen levels rose in fits and starts, driven by the competition between biological production and geological absorption. Volcanoes, still active across the continents, released gases that reacted with oxygen, consuming it as fast as microbes made it. The balance between life and rock, atmosphere and mantle seesawed for ages before stabilizing at a new equilibrium. Sedimentary records capture this slow transformation. Red beds, iron-rich rocks formed in the presence of oxygen, begin appearing in the geological record only after the Great Oxygenation. Before this time, iron existed mainly in reduced, soluble forms that did not produce rust-colored deposits. The sudden appearance of red beds marks the moment when the atmosphere itself became oxidizing, when iron on land could rust for the first time. It was as if the planet had drawn a deep breath and exhaled color. The implications for life were both devastating and generative. The mass extinction of anaerobic organisms, sometimes referred to as the oxygen catastrophe, cleared ecological niches and opened new pathways for evolution. Microbes that could tolerate or exploit oxygen spread into new environments, diversifying in structure and metabolism. Mitochondria, the energy-producing organelles within modern eukaryotic cells, likely evolved around this time through symbiosis between early aerobic bacteria and larger host cells. This partnership, one cell living inside another, allowed energy production on an unprecedented scale and laid the groundwork for all multicellular life to come. The changes also altered the planet's energy balance. With oxygen present, new forms of weathering and mineral formation became possible. Carbon began cycling differently through the crust, leading to long-term stabilization of the climate. The oceans, once dominated by dissolved iron, became clearer as iron precipitated out. This clarity allowed light to penetrate deeper, giving photosynthetic organisms more room to thrive. The biosphere expanded vertically as well as horizontally. From a planetary perspective, the Great Oxygenation was a moment of self-awareness in matter, a feedback loop that linked biology and geology inseparably. Life altered its environment, and that environment in turn altered life. For the first time, Earth became a truly interactive system, where biological processes could change atmospheric composition and climate on a global scale. This capacity for self-regulation would define the planet from that point onward. It is difficult to overstate the magnitude of this transformation. The atmosphere we breathe today, roughly 1 part oxygen to 4 parts nitrogen, exists only because of the relentless work of microscopic organisms billions of years ago. Every breath taken by every animal, every flame that burns, every drop of rust on metal is a continuation of the chemistry that began in that ancient ocean. The Great Oxygenation was the moment when Earth's air became alive. And yet, this oxygenic revolution also carries an existential paradox. The very molecule that made higher life possible was lethal to most of the life that produced it. Creation and destruction became intertwined at the molecular level. In turning the air blue, life nearly erased itself. That balance between what sustains and what endangers has persisted through every chapter of evolution since. Scientific understanding of this event continues to evolve. Studies of ancient sulfur isotopes reveal patterns that can only form in the absence of oxygen, and their disappearance in rocks younger than about 2.5 billion years confirms the atmospheric transition. Computer models of planetary chemistry show how oxygen buildup would have changed the greenhouse balance, leading to the cooling events observed in geological strata. Even the structure of modern bacterial enzymes carries traces of adaptation to that long-ago oxygen surge. To imagine the Earth during the Great Oxygenation is to see 2 worlds overlapping. One was ancient and microbial, sustained by chemistry alien to our senses. The other was emerging, bright, oxidized, and slowly recognizable as the home we know. The transition between them was not a moment but a long twilight, when seas rusted, skies cleared, and the planet learned how to breathe. When we inhale today, filling our lungs with oxygen, we participate in that same rhythm that began billions of years ago. Every atom of oxygen you breathe has passed through untold generations of photosynthetic organisms, from the cyanobacteria of the Archean to the trees of the modern Earth. The boundary between their ancient exhalation and our breath has never been broken. Perhaps this is the quiet truth of the Great Oxygenation, that the air we depend on was born of struggle, of survival amid transformation. The atmosphere that now nurtures thought and language was once a poison, and the world that turned blue did so through death as well as creation. As night falls and the air cools, you can feel the same molecules moving softly around you, ancient, recycled, patient. They whisper the memory of a time when the planet first learned to change itself, when life's smallest forms became architects of the sky. The Great Oxygenation was not just the turning of the air. It was the moment the Earth began to think, in the only way a planet can, through life itself, breathing quietly, endlessly, into time. Chapter 6. The Snowball Earth, global ice and the fragility of balance. Long after oxygen had filled the skies and rusted the oceans, Earth faced a very different kind of transformation, one born not of fire, but of cold. Around 2.5 billion years after the planet's formation, and again much later, near 700 million years ago, the world entered an era when the balance that sustained it faltered. Ice crept from the poles toward the equator, the oceans froze nearly solid, and sunlight reflected helplessly into space. It was as though the planet had fallen asleep beneath a blanket of white. Scientists call this extreme condition Snowball Earth, and it stands as one of the most extraordinary episodes in our planet's history, a test of its resilience and of life's capacity to endure when the world itself seemed frozen in time. The first known Snowball Earth is linked to the great oxygenation that reshaped the atmosphere. As cyanobacteria spread across the seas, they drew down carbon dioxide and released oxygen, altering the greenhouse balance that had long kept the planet warm. Methane, one of the most potent heat-trapping gases, was oxidized into carbon dioxide and water. Though carbon dioxide still warmed the atmosphere, it was far less effective, and the cumulative cooling proved catastrophic. With sunlight weaker in Earth's distant past and continents arranged differently than today, this shift tipped the climate toward a runaway freeze. The process unfolded slowly but inexorably. As temperatures dropped, snow and ice began to expand outward from the poles. White surfaces reflected sunlight rather than absorbing it, causing further cooling in a powerful feedback loop known as the ice albedo effect. Once glaciers reached latitudes near the tropics, the feedback became almost unstoppable. Within geological moments, the entire planet was locked in ice, from mountaintops to ocean basins. Evidence for this global glaciation lies in the geological record. Across ancient cratons from Canada to South Africa, scientists have found layers of glacial tillites, sedimentary rocks formed by ice sheets, deposited at what were once equatorial latitudes. Above these layers lie peculiar capped carbonates, thin sheets of limestone formed rapidly after the ice melted. Their presence signals a sudden and dramatic climate reversal. A frozen planet transformed back into a greenhouse world in a geological instant. To understand how such extreme transitions occurred, researchers examine the interplay of tectonics, atmospheric chemistry, and solar radiation. During these ancient episodes, continents were clustered near the equator, exposing large areas of silicate rock to weathering. Rainfall and chemical reactions drew carbon dioxide from the air, weakening the greenhouse effect and further cooling the planet. At the same time, volcanic outgassing continued at a steady rate, but the carbon dioxide it produced was rapidly absorbed by the oceans and rocks, unable to build up in the atmosphere quickly enough to counterbalance the cooling trend. As the oceans froze, global circulation nearly halted. Beneath the ice, seawater became anoxic once again, deprived of sunlight and oxygen. Hydrothermal vents continued to pump minerals into the deep ocean, but without mixing, the chemistry of the sea grew increasingly strange. Life, which had spread widely after the oxygenation of the planet, now faced extinction. Cyanobacteria, algae, and other microorganisms struggled to survive in isolated refuges, perhaps in pockets of liquid water near volcanic islands, or beneath thin ice where sunlight still filtered through. For tens of millions of years, Earth remained entombed in this frozen state. Yet even as the surface froze, the planet's internal machinery continued to operate. Volcanoes, unimpeded by ice, released vast quantities of carbon dioxide. With weathering processes nearly halted, since rain and rivers could no longer wash over rock, this greenhouse gas accumulated steadily in the atmosphere. Eventually, the concentration of carbon dioxide reached levels hundreds of times higher than anything experienced in later eras. The greenhouse effect grew immense. Slowly, imperceptibly, the ice began to melt. When the thaw came, it was sudden. Once the reflective ice receded and darker surfaces of ocean and land were exposed, sunlight was absorbed again, accelerating the warming. Massive floods carried sediments into the sea, and the supercharged greenhouse atmosphere transformed the frozen planet into one of searing heat and heavy rain. This rapid shift triggered the formation of the cap carbonates seen in ancient rock sequences, the chemical signature of a world rediscovering warmth. What followed was not simply a return to the status quo. The Snowball Earth episodes, especially those near the end of the Proterozoic eon, seem to have prepared the planet for the rise of complex life. The stress of near-total glaciation may have driven evolutionary innovation. Microbes that survived the freeze developed strategies for enduring extreme conditions, tolerance to cold, radiation, and desiccation. The subsequent flood of nutrients released by melting ice may have fueled biological expansion. In this sense, catastrophe became the catalyst for renewal. The Neoproterozoic snowball Earths, occurring between roughly 700 and 600 million years ago, are particularly significant. During these episodes, ice likely reached the equator again, leaving behind glacial deposits found today in Namibia, Canada, and Australia. The planet's rotation and tilt suggest that sunlight at the equator was still intense, yet global albedo kept average temperatures far below freezing. Models of these events show that even small changes in atmospheric composition or solar output could swing the planet from tropical warmth to global ice. Earth's climate, it seems, is a delicate instrument, tuned to balance but capable of wild extremes. In the aftermath of the last great glaciation, known as the Merino Snowball, the planet underwent a profound transformation. As the ice retreated, the oceans became oxygenated once more. Weathering of newly exposed rocks delivered phosphorus and other nutrients to the sea, stimulating photosynthetic organisms. Oxygen levels surged, paving the way for larger, more energy-demanding life forms. Not long after, in geological terms, multicellular animals began to appear in the fossil record. The earliest ancestors of everything from jellyfish to humans. The Snowball Earth hypothesis, once controversial, is now supported by multiple lines of evidence. Paleomagnetic measurements reveal that glacial deposits formed near the equator, confirming that ice extended globally. Isotopic studies of carbon and sulfur record the enormous swings in atmospheric composition that accompanied these freezes and thaws. Even the patterns of oxygen isotopes in marine sediments tell the same story. Repeated cycles of deep cold and abrupt warming. Together, they paint a picture of a planet capable of reaching both extremes of climate stability and collapse. What remains striking about these events is their timing and recurrence. Each major snowball Earth seems to have followed periods of tectonic upheaval or atmospheric change, moments when the balance between volcanic outgassing and carbon sequestration tipped slightly too far. The same feedback mechanisms that keep modern Earth stable can, under different circumstances, drive it to catastrophe. Climate, at its core, is a conversation between the planet's surface, atmosphere, and interior, and that dialogue is easily disrupted. For scientists, The study of Snowball Earth provides vital insight into planetary habitability. It demonstrates that even a planet within the habitable zone of its star can experience near total freezing if feedback loops spiral beyond control. This understanding extends beyond our own world, informing the search for life elsewhere. When astronomers examine exoplanets orbiting distant stars, they now consider not only distance from the star, but also the planet's capacity to regulate its climate, to avoid becoming a permanent snowball or an inferno. The legacy of Snowball Earth is therefore twofold. On one hand, it shows the fragility of the conditions that make life possible. On the other, it reveals the extraordinary resilience of life itself. Through these global freezes, the biosphere persisted, adapting and enduring through conditions that would annihilate most known species today. The microbes that clung to existence in the cold darkness were the ancestors of everything that followed. It is humbling to realize that all complex life, and by extension all consciousness, depends on that survival. Every tree, every animal, every human being is descended from cells that endured a frozen planet. The resilience written into their chemistry is written into ours. The same carbon dioxide that once rescued the world from eternal ice now sustains our own breath, yet also reminds us of the power we hold to alter climate again. In the deep time of the planet, warmth and cold are not opposites, but partners in a cycle of transformation. The Snowball Earths remind us that stability is never guaranteed, that balance is something the planet continually negotiates with itself. The same physical laws that froze the oceans still operate today, subtle and silent beneath the weather we take for granted. When you walk through falling snow or see frost gather on a window, you are witnessing echoes of those ancient ages when the world was locked in white. Beneath that stillness lies the story of survival of a planet that refused to die. The ice receded, the seas awakened, and from the silence of that frozen world came the warmth of new beginnings. And perhaps that is the deeper reflection to carry forward, that life endures not because the universe guarantees it, but because it learns to adapt even when the light dims. The earth, wrapped once in ice, found its balance again, and within that balance it found us. Every breath of air, every drop of rain, every living thing carries the memory of that long winter and the quiet triumph that followed, the day the planet thawed and began once more to dream. Chapter 7. The Cambrian Explosion. Life Discovers Complexity. After the long reign of simplicity that defined most of Earth's history, the planet entered an era that changed everything. For billions of years, life had remained microscopic. Cells drifting through the oceans, forming thin mats on the seafloor, and quietly shaping the atmosphere. But around 540 million years ago, the biosphere began to quicken. In a geologically brief interval, no more than a few tens of millions of years, the world went from microbial to magnificent. Organisms developed bodies, eyes, shells, and skeletons. Predators and prey appeared for the first time. Ecosystems became layered and dynamic. This remarkable transition, known as the Cambrian Explosion, marked life's discovery of complexity. The causes of this explosion remain one of the most fascinating puzzles in evolutionary biology. It was not a sudden miracle, but rather the culmination of deep, slow processes that had been preparing the planet for ages. Oxygen levels in the atmosphere and oceans had finally reached a critical threshold, allowing for higher metabolic rates and more complex body structures. The breakup of the supercontinent Rodinia created shallow continental seas where sunlight could penetrate and nutrients circulated freely. In these fertile shallows, evolution found both opportunity and motive. By the beginning of the Cambrian period, the stage was perfectly set. Oxygen made energy-rich metabolisms possible. Calcium and other minerals were abundant in seawater, providing the raw materials for skeletons and shells. Genetic mechanisms such as the development of Hox genes, those that control body patterning, had already evolved in simpler organisms. When environmental and genetic readiness met, diversity exploded. The fossil record of this time provides a vivid glimpse into life's creative outburst. Nowhere is it better preserved than in the Burgess Shale of Western Canada, where fine-grained mud captured the details of soft-bodied creatures with astonishing precision. In these rocks, scientists have uncovered a gallery of forms that seem almost surreal. Animals with feathery limbs, stalked eyes, serrated claws, and elaborate mouthparts. Anomalocaris, one of the earliest apex predators, swam through the Cambrian seas using undulating flaps, its ringed mouth lined with teeth. Nearby swarmed Opabinia, with 5 eyes and a flexible proboscis tipped with grasping claws. Trilobites, armored arthropods with compound eyes, scuttled across the seafloor in great numbers, leaving trails that can still be traced in stone. What makes the Cambrian so extraordinary is not just the appearance of new species, but the birth of new body plans, entirely novel architectures for life. Almost all of the major animal groups that exist today trace their origins to this period. Arthropods, mollusks, chordates, annelids, echinoderms, and more. The basic blueprints for modern anatomy were drawn here, and though refined across 500 million years, the fundamental patterns remain. You, reading this now, carry within your body the echoes of Cambrian innovation. A head with sensory organs, a spine-like axis, and bilateral symmetry that first evolved in those primeval seas. The reasons for this evolutionary acceleration are complex. One contributing factor was ecological interaction itself. Once some organisms began to move, burrow, or hunt, they altered the environment for others. The seafloor, previously covered in stable microbial mats, was stirred and oxygenated. Predation drove the development of defense, shells, spikes, and mobility. Eyes evolved to spot danger or prey, setting off an evolutionary arms race that favored sensory sophistication and faster neural responses. Every new adaptation created selective pressure for another, and the result was an escalating feedback loop of diversity. The rise of biomineralization, using minerals to create hard structures, was a turning point. Skeletons and shells offered protection, leverage for muscles, and new opportunities for locomotion. They also dramatically increased the likelihood of fossilization, allowing us to see the Cambrian world in far greater detail than the soft-bodied ages before it. Tiny fragments of calcium phosphate and carbonate from early shells appear in the rock record just before the explosion, suggesting that life was already experimenting with ways to solidify its form. Geochemical evidence supports the idea that environmental stability played a role as well. Before the Cambrian, the planet had endured cycles of severe glaciation, the Snowball Earth events. As the climate warmed and stabilized, nutrient runoff from melting glaciers enriched the oceans, stimulating photosynthesis and oxygen production. With higher oxygen levels and abundant food, ecosystems could support larger, more active creatures. The Cambrian seas themselves would have been astonishing to behold. Coral-like reefs of microbial and sponge communities stretched across the continental shelves. In the clear, shallow waters swam strange jellyfish, early worms, and armored predators. Soft-bodied creatures glided through the water using cilia or fins, while burrowing organisms tunneled through the sediment below, creating a newly dynamic ecosystem. For the first time, life was not confined to passive existence. It moved, hunted, hid, and interacted. Amid this biological renaissance, one lineage began to show the earliest hints of what would become the vertebrate body plan. Small fish-like creatures with flexible rods of cartilage along their backs, structures that would later evolve into spines, appeared in the fossil record. These primitive chordates, such as Pacaya, represent the distant ancestors of all animals with backbones, from amphibians and reptiles to mammals and humans. The appearance of such forms illustrates a broader truth. The Cambrian explosion was not merely a proliferation of shapes, but a deep restructuring of how life organizes itself. As ecosystems grew more complex, so too did the cycles of energy and matter within them. Nutrient recycling, predation, and symbiosis all intensified. This complexity began to affect the planet's chemistry on a global scale. Carbon was drawn more efficiently into sediments, altering the composition of the atmosphere. The biosphere had become a powerful geological force, capable of reshaping the environment that sustained it. Despite its name, the Cambrian explosion was not instantaneous. Modern dating techniques reveal that diversification unfolded over perhaps 20 to 30 million years, a blink in geological time, yet long enough for evolution to test countless possibilities. Some experiments in form were dead ends, leaving behind bizarre fossils with no modern descendants. Others succeeded, refining the patterns that would dominate for the rest of Earth's history. By the end of the period, the world teemed with life far more diverse and interactive than anything seen before. Why the explosion eventually slowed remains a matter of debate. Once ecological niches were filled, selective pressures may have stabilized, reducing the rate of innovation. Environmental conditions likely changed, with nutrient levels and oxygen settling into new equilibria. The rapid burst of novelty gave way to a more gradual pace of evolution, but the foundation of complex life had been established forever. To scientists, the Cambrian explosion remains a reminder of how nonlinear evolution can be. For billions of years, life lingered in simplicity, and then, within a narrow window of time, it radiated into nearly every conceivable form. It demonstrates that the potential for complexity was always there, waiting for the right combination of genetic and environmental conditions. The explosion was not inevitable, but it was possible, and once it began, it reshaped the course of the planet's story. Today, we study the Cambrian world not only through fossils, but through molecular clocks, comparisons of genetic divergence among living organisms. These analyses reveal that many lineages existed long before they appeared in the rock record. The explosion, then, may have been as much a revelation of form as an origin of it, a point when evolutionary experiments finally became visible in the sedimentary archive. Still, the rapid diversification recorded in stone speaks to something extraordinary. A planet discovering what life can do when energy, oxygen, and innovation align. In existential terms, the Cambrian explosion is more than an evolutionary milestone. It is the first flowering of biological imagination. From the chemistry of cells came sensation, motion, and behavior. The first eyes saw the light of the sun reflected in the ocean. The first muscles moved a body through space. The first nervous systems processed information and made choices, however primitive. In those moments, the Earth itself became aware of its environment in a new way, through the countless perceptions of living beings. It is humbling to consider that all consciousness, all thought and experience descend from that explosion of complexity. The human brain, the forest's network of roots, the sensory world of birds and whales, all are elaborations of systems that first emerged in those ancient seas. The blueprint for awareness was written in the Cambrian mud. If you could stand on a Cambrian shoreline, you would see a world at once alien and familiar. Waves would crash over reefs, teeming with creatures whose shapes defy imagination. Sunlight would scatter through clear oxygenated water filled with shimmering plankton. Beneath the surface, the seafloor would move as burrowers reshaped it grain by grain. It was the first time in Earth's history that beauty, as we might recognize it, filled the world. A dynamic, colorful, ever-changing interplay of form and motion. And as you breathe now, remember that your lungs, your blood, your senses, all the intricate mechanisms that make you alive, are direct descendants of that Cambrian burst. Life discovered how to see, to move, to defend, to pursue, and eventually to reflect. In that sense, the Cambrian explosion never truly ended. Its echoes live on in every living thing, in every moment of perception and awareness. The Earth, once a silent sphere of rock and water, began to pulse with complexity and interaction. The Cambrian marked the moment when the planet learned to express itself in form and motion, when the long simplicity of the past gave way to the restless creativity of evolution. And from that creativity came everything: the forests, the oceans, the birds, and the mind reading these words. All of it began in that deep blue dawn, when life discovered how to become more than survival, when it discovered how to be. Chapter 8. The Age of Giants: Continents, Dinosaurs, and Changing Worlds. After the Cambrian seas gave rise to life's first great diversity, the planet continued to evolve on scales so vast that entire continents came and went. Across hundreds of millions of years, the surface of Earth reshaped itself again and again. Mountains rose, oceans opened and closed, and the climate oscillated between extremes of heat and cold. Amid this geologic theater, life adapted and expanded into every environment, from the ocean's depths to the highest plains. This long stretch of time, covering the Paleozoic, Mesozoic, and early Cenozoic eras, is often called the Age of Giants. It was an age when continents collided, ecosystems flourished, and creatures of astonishing size and beauty ruled the land, sea, and sky. At the dawn of this age, the continents were scattered fragments drifting across a watery planet. Through the slow dance of plate tectonics, they converged to form supercontinents, first Gondwana, then Pangaea. When these landmasses collided, mountains as vast as the Himalayas rose from the Earth's crust, and volcanic eruptions filled the air with ash and carbon dioxide. The rearrangement of continents shaped both climate and evolution. When all land was joined together in Pangaea, deserts spread across its interior, while coastlines teemed with new life. The isolation and later breakup of this supercontinent created barriers and opportunities that would guide evolution's course for millions of years. During the Paleozoic era, life conquered the land. Plants developed vascular tissues that allowed them to grow upright and transport water, forming the planet's first forests. Insects followed, then amphibians, vertebrates that could breathe both in water and on land. By the late Carboniferous period, vast swampy forests covered much of the equatorial world, storing immense amounts of carbon in the form of peat, and coal. Oxygen levels soared to heights not seen before or since, supporting giant dragonflies with wingspans wider than a hawk's and millipedes the length of a human. It was an age of abundance, but also of fragility. Mass extinctions punctuated this rise of life. The most devastating occurred at the end of the Permian period, about 250 million years ago, when nearly 90% of all species vanished. This catastrophe, triggered by massive volcanic eruptions in what is now Siberia, released vast amounts of carbon dioxide, causing ocean acidification, global warming, and a collapse of ecosystems. Yet life endured. From the ashes of extinction, new forms emerged, smaller, adaptable, ready to fill the empty niches left behind. Out of this rebirth came the Mesozoic era, the true heart of the Age of Giants. It began with a recovering biosphere and ended with one of the most famous extinctions in history. But in between, life achieved some of its most spectacular forms. During the Triassic period, reptiles diversified rapidly, giving rise to the ancestors of dinosaurs, crocodiles, and birds. Within tens of millions of years, dinosaurs became the dominant life forms on land, evolving into a stunning array of shapes and sizes. By the Jurassic period, Earth's climate was warm and humid, with high levels of carbon dioxide fostering lush vegetation. Giant conifer forests stretched across the continents, and ferns carpeted the ground. In these verdant landscapes walked creatures that would define the era. Sauropods with necks longer than buses, stegosaurs with plates along their backs, and theropods that stalked prey with keen eyes and sharp claws. In the skies above, pterosaurs mastered flight, their wings stretching on membranes of skin. In the seas, ichthyosaurs and plesiosaurs hunted through ancient oceans that teemed with ammonites and plankton. The Mesozoic Earth was a living engine of motion and balance. Herbivores and carnivores shaped one another's evolution in a constant arms race of adaptation. The warm, oxygen-rich atmosphere supported enormous body sizes and metabolic rates far higher than earlier reptiles could sustain. Some dinosaurs evolved feathers, first for insulation, later for display, and finally for flight. From those feathered theropods emerged the first true birds, creatures that still carry echoes of the giants they descended from. Throughout this age, the continents were not static. Pangaea began to fracture, drifting apart under the slow force of plate tectonics. New oceans opened where rifts tore through the crust, dividing ecosystems and isolating populations. The Atlantic Ocean, for instance, was born in this era, its widening shape pushing Europe and the Americas ever farther apart. This gradual fragmentation increased biodiversity as species adapted to the new climates and environments that arose along continental margins. Volcanic activity, driven by the same tectonic forces, released carbon dioxide into the atmosphere, maintaining the greenhouse conditions that kept the planet warm. Polar ice was absent and sea levels were high, flooding low-lying regions and creating shallow inland seas. These environments provided fertile breeding grounds for marine life, including the ancestors of modern fish and marine reptiles. Coral reefs expanded dramatically, hosting ecosystems as rich and complex as those of the modern tropics. Yet even during this flourishing, instability lingered beneath the surface. Periodic volcanic outbursts caused climatic fluctuations, and asteroid impacts occasionally disturbed the balance. Still, life's diversity increased, filling nearly every ecological niche. Mammals, small and nocturnal, lived in the shadows of the dinosaurs, awaiting their turn in the evolutionary narrative. Then, around 66 million years ago, the balance broke once again. A massive asteroid struck near the present-day Yucatan Peninsula, releasing energy equivalent to billions of atomic bombs. The impact vaporized rock, ignited global wildfires, and sent dust and sulfur into the atmosphere, blocking sunlight for years. Photosynthesis collapsed, the food chain unraveled, and the giants of the Mesozoic, both in the sea and on land, vanished. The age of dinosaurs ended abruptly, leaving only their descendants, the birds, to carry their lineage forward. In the aftermath came the rise of mammals. Freed from competition, they diversified rapidly during the early Cenozoic era. Some returned to the oceans, evolving into whales and dolphins. Others grew to enormous sizes on land, elephants, rhinos, and mammoths, while smaller species adapted to every imaginable environment. Forests spread across the continents, then retreated as climate cooled. Grasses evolved, giving rise to vast savannas and grazing animals. Through all these changes, life continued its restless experimentation with form and function, each adaptation a response to shifting continents and climate. The Earth itself also continued to evolve. The collision of the Indian and Asian plates gave rise to the Himalayas, reshaping global weather patterns. Ice sheets formed at the poles, initiating the first long-term ice ages since the planet's early history. Ocean currents reorganized, carrying heat between hemispheres and influencing ecosystems on a planetary scale. The balance between tectonics, atmosphere, and biology became ever more intricate. From a geological perspective, the Age of Giants represents the maturation of the planet's biosphere. Life was no longer fragile or confined to narrow environmental limits. It could withstand heat, cold, drought, and flood. It could move, migrate, and adapt. Every extinction opened new opportunities. Every climate shift rewrote the rules of survival. Through these cycles, the diversity and resilience of life deepened. Paleontologists studying this vast era rely on fossils, isotopic dating, and sedimentary layers to reconstruct the changing world. The distribution of ancient plant and animal fossils across continents provides direct evidence for plate tectonics. The chemical composition of rocks reveals the climate of vanished ages, the warmth of the Mesozoic greenhouse, the chill of later ice ages. Each layer of Earth's crust tells part of the same continuous story, life and planet evolving together in a delicate dialogue. And in this dialogue lies a lesson that extends beyond prehistory. The giants of Earth's past remind us that no dominance lasts forever. Species rise and vanish, continents drift, climates shift, and the planet continually rebalances itself. Extinction, in this light, is not failure but transformation, a clearing of the stage for new possibilities. The disappearance of the dinosaurs paved the way for mammals, just as the earlier extinctions of the Permian and Devonian had opened paths for others. The great cycles of Earth's history, creation, flourishing, collapse, and renewal, mirror processes we see on every scale, from galaxies to cells. Life adapts, but it also remembers. The genetic instructions that built the first vertebrates are still written within us, refined but unchanged. When we study fossils of titanic reptiles or ancient forests, we are looking not at strangers, but at the older chapters of our own story. If you could stand on a Mesozoic plain, you would see herds of sauropods moving like mountains against a horizon of cycads and conifers. You would feel the ground tremble under their weight and hear the distant call of pterosaurs gliding above volcanic ridges. The air would be heavy and warm, the sky filled with unfamiliar stars. Yet even then, the seeds of your existence were there. In the tiny mammals hiding beneath ferns, in the chemical cycles that bound atmosphere to ocean. In the end, the Age of Giants was not just a time of enormous creatures, but of immense transitions. It demonstrated how tightly intertwined geology and biology have always been, and how each depends on the other for renewal. From the molten continents of the Triassic to the flowering plains of the Cenozoic, Earth proved its ability to reinvent itself without ever stopping its motion. And as we look back from our brief vantage point in time, we inherit not the grandeur of the dinosaurs, but their legacy of adaptation. The same Earth that once nurtured them now sustains us, and it too will change beyond our imagining. Perhaps that is the truest continuity, the rhythm of impermanence itself. The Age of Giants reminds us that life's greatness lies not in permanence, but in the persistence to begin again. Chapter 9. The Rise of Mammals, from Ashes to Intelligence. When the Age of Giants ended, the Earth was quiet. The asteroid that struck near what is now the Yucatan Peninsula had left a planet in ruins. The air was choked with dust and soot. Sunlight dimmed to twilight for months, perhaps years. Photosynthesis collapsed. Forests withered. The seas turned toxic from falling debris and acid rain. In that prolonged darkness, 3/4 of all species perished, including nearly every non-avian dinosaur. Yet from that silence came renewal. When the light returned, life began again. And among the survivors, a small, warm-blooded lineage that had lived in the shadows for millions of years was ready to inherit the Earth. Mammals had existed long before the asteroid's arrival. Their ancestors diverged from reptilian lineages during the late Triassic period, over 200 million years earlier, evolving alongside dinosaurs. But for most of that immense span, they remained small, nocturnal, and unobtrusive, creatures of the undergrowth and night. They had survived by occupying ecological niches that larger animals ignored. With sharp hearing, warm blood, and the ability to regulate body temperature, they were well suited to the darkened, unstable world that followed the impact. The earliest mammals were remarkable in their subtlety. Their lineage had evolved traits that set them apart from the reptiles dominating the Mesozoic. They possessed differentiated teeth, incisors, canines, and molars, allowing them to process a wide variety of food. Their jaws had changed too. The bones that once formed part of the reptilian jaw had shifted into the middle ear, giving them an extraordinary sensitivity to sound. They nursed their young with milk and insulated their bodies with fur. These seemingly modest adaptations became the foundation of resilience, allowing mammals to persist through catastrophe. In the aftermath of the extinction, the world was open. With the great reptiles gone, the competition for resources vanished almost overnight. Ecosystems began to rebuild, starting with the smallest plants and insects. Mammals, adaptable and warm-blooded, thrived in this shifting landscape. Within a few million years, they diversified into new forms, evolving to fill the empty ecological niches once ruled by dinosaurs. Some took to the trees, others to the water, and many to the open plains that were beginning to spread across the continents. During the Paleocene and Eocene epochs, the Earth's climate was warm and stable, fostering rapid diversification. Forests blanketed the continents from pole to pole, and mammalian life radiated outward in astonishing variety. Herbivorous species evolved broad, grinding teeth to process vegetation, while carnivores developed sharper claws and keen eyesight. Whales and dolphins emerged from land-dwelling ancestors, returning to the oceans that had once given rise to all vertebrate life. On land, the first large mammals appeared, ancestors of elephants, rhinos, and horses. Evolution seemed to accelerate, testing endless variations of form and behavior. The success of mammals was rooted in physiology as much as opportunity. Endothermy, the ability to maintain a constant internal temperature, allowed them to inhabit a wide range of environments. Complex brains supported learning and social behavior. Extended parental care gave offspring higher survival rates, enabling slower but more refined development. These characteristics laid the groundwork for intelligence, cooperation, and adaptability, the traits that would one day define the human species. Meanwhile, the continents continued their slow drift. The collision of India with Asia raised the Himalayas, reshaping global weather and monsoon cycles. South America, still isolated, became a laboratory of evolution, producing unique species like giant ground sloths and terror birds. In Africa, tropical forests alternated with savannas as climates fluctuated, influencing the evolution of primates, the lineage that would eventually give rise to us. The Eocene world was lush and full of warmth, but nothing on Earth remains constant. Around 34 million years ago, the planet began to cool. Ice first appeared in Antarctica, and sea levels fell. Forests retreated, giving way to grasslands and open plains. In response, mammalian life adapted once again. Grazing animals with high-crowned teeth evolved to feed on abrasive grasses, while predators became faster and more agile to chase them. The evolutionary story of the mammals was one of continual reinvention, guided by climate and geography. Among the most significant developments of this era was the emergence of primates with increasingly complex brains and dexterous hands. The first true monkeys and apes evolved in Africa and Asia, displaying curiosity, social organization, and the capacity for learning. Over millions of years, as climates shifted and habitats fragmented, some of these apes descended from the trees to walk upright. The stage was being set for the rise of hominins, but that would come much later. For now, the planet belonged to the mammals in all their diversity. Elephants roaming grasslands, whales singing in the oceans, and bats filling the night sky. One of the keys to this evolutionary success was flexibility. Mammals could adjust their behavior to changing conditions, rather than relying solely on slow genetic adaptation. They could seek shelter, hunt cooperatively, or migrate to more favorable climates. The development of larger brains enabled them to process information and learn from experience, allowing cultural transmission, an early form of what we now call knowledge. Intelligence was not yet consciousness as we know it, but it was its foundation. The fossil record shows how profoundly mammals reshaped the biosphere. In the absence of dinosaurs, they filled ecological roles at every level of the food chain. Herds of herbivores maintained grasslands, influencing atmospheric carbon levels. Predators like saber-toothed cats and large bears regulated populations of prey, maintaining balance in ecosystems. Even burrowing rodents and small insectivores altered the soil, affecting plant distribution and nutrient cycles. The world itself became, in a sense, a mammalian planet. Yet the history of mammals is not a story of uninterrupted progress. The Cenozoic era saw its share of extinctions and upheavals. Volcanic eruptions, shifting climates, and asteroid impacts continued to test life's resilience. During the Pleistocene epoch, the planet entered a new rhythm of glacial cycles, periods of advancing and retreating ice that reshaped continents and sea levels. In this harsh, unstable world, mammals adapted again. Thick fur, hibernation, and migration became survival strategies. Some, like mammoths and woolly rhinoceroses, grew to immense sizes to withstand the cold. Others, like our own ancestors, adapted through intelligence and cooperation. The evolution of mammals represents more than the triumph of one group of animals. It reflects the deepening relationship between biology and cognition. From sensory awareness came communication, from communication came cooperation, and from cooperation came culture. This slow expansion of mind through matter is one of the most profound outcomes of evolution. It suggests that intelligence is not an anomaly, but a continuation of life's drive toward complexity and awareness, a process that began long before humans walked the earth. Scientific understanding of this evolutionary arc is drawn from fossils, molecular genetics, and comparative anatomy. DNA analyses confirm the relationships among mammalian groups, tracing lineages back through the branching tree of life. The structure of the mammalian brain, with its layered cortex and capacity for memory and imagination, is itself a fossil of this journey, a biological record written in neurons instead of stone. Every heartbeat, every breath, every reflex in a modern mammal carries the signature of this long, adaptive history. As the Pleistocene gave way to the Holocene, the last great ice sheets retreated and ecosystems stabilized once more. Many of the giant mammals of the Ice Age, mammoths, saber-toothed cats, giant sloths, vanished, driven by climate change and increasingly by the actions of one newly ascendant species. Humanity emerged not as a replacement for the giants, but as their inheritor, the continuation of the same evolutionary story. It is tempting to view this rise of intelligence as destiny, but in truth, it was the product of chance and circumstance. A slightly different asteroid trajectory, a few degrees of climate variation, or a random mutation unexpressed could have rewritten the outcome. The mammals did not conquer the Earth through superiority, but through adaptability. They thrived not by domination, but by resilience, the same quality that allowed the first small shrew-like creatures to survive the darkness that ended the dinosaurs. The rise of mammals, then, is not only a biological tale, but a philosophical one. It shows that intelligence emerged from fragility, that awareness grew out of survival. The brain, that intricate organ capable of reflection, was sculpted by fear, hunger, and curiosity. The consciousness that now wonders about its own origins was born from countless generations of adaptation and chance. If you could watch the Earth across these epochs, you would see forests expanding and retreating, ice advancing and melting, continents drifting imperceptibly through time. You would see herds migrating beneath red sunsets, predators moving through the grass, whales gliding through dark waters that echo with their songs. And you would know that every sound, every motion, every breath was part of the same long experiment, the universe exploring itself through living matter. Today, when you look into the eyes of another mammal, a dog, a whale, a primate, you see not just resemblance, but continuity. The same nervous spark, the same evolutionary memory, the same thread of awareness that began when small creatures survived a planet in ruin. Their story is our story, written across millions of years in bone, fur, and thought. The mammals rose from ashes and learned to think. In doing so, they transformed not only the world, but the meaning of existence upon it. From the silence after destruction came heartbeat and mind, and from the struggle to survive came the capacity to imagine. The age of mammals is not merely an age of animals, it is the age of reflection, of the planet knowing itself through the fragile miracle of life. Chapter 10. The Present Moment, a living planet aware of itself. Across billions of years, through fire, ice, and extinction, Earth has never ceased to transform. What began as dust circling a young star has become a world of continents, oceans, and life. The planet has cooled, cracked, and healed countless times, yet it endures in a dynamic equilibrium between destruction and renewal. Every rock, river, and breath of air bears the imprint of that evolution. And now, for the first time in its long history, Earth looks upon itself, not through volcanic plumes or shifting tides, but through the consciousness of the beings it has produced. The present moment is not a single point in time, but a culmination, a convergence of processes stretching back to the beginning. The oxygen you breathe was forged by ancient cyanobacteria. The calcium in your bones condensed in a long-dead star. The silicon in your devices once drifted in interstellar space. Humanity, with all its complexity, is the latest expression of a pattern that began in cosmic chemistry and continued through molecular self-organization, cellular life, multicellularity, and sentience. When viewed on geological timescales, the emergence of intelligent life is not separate from planetary evolution. It is its continuation. The Earth we inhabit today is a profoundly interconnected system. Its atmosphere, hydrosphere, biosphere, and geosphere operate in feedback loops that maintain the delicate balance of climate and chemistry. Oceans absorb heat and carbon dioxide, regulating temperature. Plants release oxygen while capturing carbon, influencing atmospheric composition. Even microscopic organisms buried in soil or drifting in the sea play vital roles in recycling elements essential for life. This self-sustaining interaction is what scientists call the Earth system, a vast network of physical and biological processes that, in effect, makes the planet behave almost like a single organism. Some thinkers have described this idea as the Gaia hypothesis, proposing that life and the environment evolve together as a unified system. Though the term Gaia evokes mythology, the underlying concept is scientific. Feedback mechanisms between living and non-living components can stabilize conditions conducive to life. Photosynthesis, weathering, and ocean circulation all participate in this planetary regulation. While not conscious in any human sense, the biosphere's collective behavior creates the appearance of purpose, an equilibrium born from interaction rather than design. Yet this equilibrium is fragile. The same processes that once drove glaciations and greenhouse ages now unfold at a scale accelerated by human activity. In only a few centuries, the species that evolved from forest-dwelling primates has become a geological force, altering the chemistry of the atmosphere and oceans faster than natural systems can adapt. The burning of fossil carbon, accumulated over hundreds of millions of years, releases greenhouse gases that trap heat and disturb climate stability. Deforestation, pollution, and habitat loss reshape ecosystems that took eons to evolve. Humanity has become both the caretaker and the disruptor of the biosphere, the first species capable of understanding planetary change, and the first to cause it knowingly. From a scientific standpoint, we live in what many geologists propose to call the Anthropocene, the epoch in which human influence dominates geological and ecological systems. Ice cores, ocean sediments, and rock strata will one day bear unmistakable traces of our presence. Radioactive isotopes from nuclear testing, plastics preserved in marine layers, and shifts in carbon ratios reflecting industrial emissions. These markers are not simply evidence of activity. They are the geological signature of cognition. a record of a planet that has become aware of its own transformation through the actions of one of its inhabitants. Despite this disruptive power, life remains astonishingly resilient. The planet has faced global extinctions before and recovered, though never with such an intelligent participant in the equation. Modern science offers unprecedented insight into the workings of climate, genetics, and ecosystems. Satellites measure the planet's pulse in real time, its temperature, vegetation, and atmospheric currents. Laboratories trace the molecular foundations of life back to the simplest cells. Humanity now observes from a vantage point once reserved for time itself, able to perceive both the planet's ancient past and its potential futures. The biosphere today holds an immense range of life forms, from single-celled extremophiles in volcanic vents to blue whales that traverse entire oceans. Every organism, however small, participates in the same vast biochemical cycle of energy and matter. DNA links all living things, carrying a record of evolution written in the same four-letter alphabet. When a tree exhales oxygen, when coral builds its skeleton, when you take a breath, each is part of a continuous conversation between biology and environment. The modern Earth is alive not because of any single organism, but because of the interconnected totality of all of them. And within that web of life stands a peculiar branch, humans, capable not only of shaping their environment, but of imagining it. In the grand context of planetary time, our species is unimaginably young. Anatomically modern humans appeared less than 500,000 years ago, a fleeting instant compared to the 4.5 billion years of Earth's existence. Yet in that blink of time, we have developed language, technology, and science, tools that allow us to perceive the universe at scales from the quantum to the cosmic. Through our eyes, the planet has begun to study itself, and through our minds, it has begun to understand its own fragility. Our civilization depends entirely on the ancient systems that sustain life. The thin atmosphere, the circulation of oceans, the fertility of soils, and the stability of climate. These are not infinite resources, but dynamic balances maintained through delicate feedbacks. Carbon drawn from the air by photosynthesis is stored in forests and oceans. When those reservoirs are disturbed, the equilibrium shifts. Understanding this interdependence has become one of science's greatest challenges and perhaps humanity's most urgent moral question. The scientific narrative of the present moment is one of feedback and awareness. We can trace the flow of carbon through the atmosphere, measure the retreat of ice, and model the migration of species as climate zones shift. The data are clear. The planet is warming, biodiversity is declining, and ecosystems are under pressure. Yet the same intelligence that caused these disruptions also grants us the means to mitigate them. Renewable energy, conservation, and global cooperation reflect not only technological progress, but an awakening of planetary self-awareness. A recognition that humanity's fate and the Earth's health are inseparable. In this sense, the emergence of intelligence can be seen as a new phase in planetary evolution. Just as photosynthesis once transformed the atmosphere, cognition now transforms the biosphere. Through knowledge, the planet has developed a reflective layer, an awareness capable of understanding and choosing. Whether that awareness will sustain or destabilize the system remains uncertain. Evolution has no direction except survival, and intelligence, like oxygen before it, is both creative and destructive. It can preserve or consume, nurture or erase. What remains scientifically undeniable is that Earth is still a living world. Its systems pulse and change with rhythm. Tides, seasons, migrations, and weather patterns all move in cycles shaped by celestial mechanics and internal dynamics. Even in the Anthropocene, these cycles continue, though distorted. The planet will adapt to whatever comes next, as it always has. But the question that defines this epoch is whether humanity will adapt with it or against it. When astronauts first saw Earth from space, they described it as fragile, luminous, and alone, a blue sphere floating in darkness. From that perspective, national borders, histories, and divisions vanish. What remains is a single shimmering ecosystem, self-contained and self-aware. That image is not merely symbolic. It is scientific truth. Everything we know, every material we use, every thought we have, arises from this one planet. The carbon in your cells was once part of the atmosphere, the oxygen in your blood part of the oceans, and the metals in your devices part of the crust. The boundary between humanity and planet is therefore not real. It is conceptual. We are the continuation of geological and biological evolution, not its observers, but its expressions. Modern science continues to deepen this perspective. Ecology reveals that no species exists in isolation. Quantum physics shows that even at the smallest scales, matter is interconnected and probabilistic. Cosmology reminds us that Earth itself is temporary, one among countless worlds orbiting countless stars. And yet this fragile sphere is the only known place where the universe has become conscious. When life looks outward to study the cosmos, it is, in a sense, the cosmos studying itself. To live in this era is to inhabit a paradox. We hold immense power to alter the world, yet our understanding shows us how small we truly are. The forces that shaped continents and species operate on timescales beyond imagination, while our civilizations rise and fall in mere moments by comparison. Still, in that briefness lies meaning. The awareness that can contemplate 4 billion years of history exists only because those years unfolded exactly as they did. When you breathe tonight, consider that the air entering your lungs carries atoms that once cycled through ancient forests, through dinosaurs, through the oceans of the Archean and the volcanic skies of the Hadean. Every molecule is a traveler through time. Every heartbeat is powered by energy that originated in the core of a distant star. The present moment is therefore not separate from the past. It is the universe's latest expression of continuity. And perhaps that is the quiet revelation of this age, that Earth, once molten and lifeless, has become capable of reflection. Through us, it knows that it exists. Through our science, it measures its orbit, its composition, its origins. Through our art and thought, it dreams of futures. Whether those dreams will preserve or consume the planet is a question still being written, moment by moment. The story of Earth is not over. It has simply reached a new chapter, one in which the narrator is also the subject. The living planet, aware of itself, continues to change, and as the night settles and you look up at the stars, you are witnessing that awareness in motion. The universe, vast and ancient, quietly recognizing its own existence through the consciousness of one small world that learned to see. You made it to the end, my friend. If your eyes are still open, another journey is waiting. Explore the next story, or let the stars keep you company while you rest. Sweet dreams among the stars.